Okay, in this discussion we're going to learn how to calculate heats of reaction in a couple different ways. We're also going to talk about reaction spontaneity, and with that we're going to talk a little bit about entropy. Okay, so when we talk about thermochemical reactions, basically we're looking at a balanced equation that includes the energy exchange either within the equation, like plus 100 kilojoules, or written on the outside of the equation as delta H. So here's an example. This is the synthesis of sulfur trioxide from sulfur dioxide and oxygen, and the enthalpy is written outside the equation. You could also write it, since this is exothermic, we know that because delta H is negative, you could also write it as a product. Now, the change in enthalpy is proportional to the amount reacting, right? So if I reacted 1 mole of a substance, it would produce less heat than if I reacted 10 moles of the substance. So this is 198 kilojoules is produced when this reaction happens. So when 2 moles of sulfur dioxide react with a mole of oxygen to produce 2 moles of sulfur trioxide. So I have related conversions from that. Okay, so let's look at this problem. How much heat would be released if you made 25 grams of sulfur trioxide? The molar mass is 80.07. Okay, so we can again set this up using dimensional analysis. All right, so we'll start with what we're given, which is 25.0 grams of sulfur trioxide, convert to moles, and then we know for every 2 moles of sulfur trioxide, we release 198 kilojoules. So the answer we'd get is negative 30.9 kilojoules. Another way of saying that is that 30.9 kilojoules are released. Okay, now let's talk about Hess's law. So this is a way of calculating heat of reactions using multiple equations. So the heat of an overall reaction is the same as the sum of the heats of smaller reactions that add up to the overall reaction. That in itself is a very confusing statement, but you'll see what we mean by that. So we're going to be given reactions, and we have to manipulate those reactions to add up to our final goal reaction. So there's 2 real ways we can do this. We can reverse the direction of the reaction, and in so doing, we'd reverse the sign of the enthalpy associated with that reaction. And we can multiply or divide the reaction by a number. Okay, and we would, whatever operation we do to the reaction, we would do that to the enthalpy. And one more note on Hess's law, it's kind of useful if a reaction is sort of difficult to measure directly, we could then look at smaller reactions. Okay, so this is the reaction we looked at before, the synthesis of sulfur trioxide. So if we wanted to reverse this reaction, we would write it as the decomposition of sulfur trioxide, and the enthalpy of that process is positive 198 kilojoules per mole. If we needed the coefficients to change, so if we needed the coefficient of sulfur dioxide to be 1, we could multiply all the coefficients by half, or divide them by 2, depending on which way you want to look at it, and then we would do the same thing to the enthalpy. Okay, so let's look at an example, the combustion of methane gas. So we're going to find the heat of this reaction, and we're not going to actually use numbers here. We're going to use A, B, and C to represent the enthalpies. Okay, so to figure this out, we're basically trying to make those reactions match the overall reaction. Okay, so our first reactant in the overall reaction is methane. Okay, so we have to figure out where we see methane. All right, so I see it in reaction A. Now I have to ask myself 2 questions. One, is it on the correct side of the equation? It's not. It's on the product side. We need it on the reactant side. And 2, does it have the correct coefficient? Okay, yes, it does. All right, so all I need to do for reaction A is reverse it. Okay? So I've reversed reaction A, and so I'm going to change the sign of the enthalpy associated with that process. Okay? Now, oxygen is next, but if you look carefully, we have oxygen in 2 different equations. So we're going to skip that for now, and we're just going to assume that it's going to work itself out at the end. Okay? So let's move on. Carbon dioxide. Carbon dioxide is in equation B. It's on the correct side of the equation, and it has the correct sign, so we can use B as is. Okay? And finally, our last product is water, 2 waters. Okay, so we see water in equation C. It is on the correct side of the equation. However, it has a coefficient of 1. So we're going to multiply everything in equation C by 2. And then we're also going to multiply the enthalpy by 2. So if we wanted to get the heat of this reaction, we would do negative A plus B equals 2C. Now I want to show you how all of these little equations, when I add them together, give me my overall equation. So I added those all together, and I took all the reactants from A, B, and C and put them on the left side of the equation. Notice that I combined like terms, so I have two O2s coming from here. Okay, and then on the right side of the equation, the product side, I have all the different products. And now if something appears on both sides of the equation, I can cancel it out. So carbon is on both sides of the equation, as are two hydrogens. So then what's left is the same as my overall equation here, just to prove that this works. Okay, and so my enthalpy value would be negative A plus B plus 2C. If you're not sure if you've done an equation right, this is a good thing to do just to double check. If you're pretty confident, you don't necessarily have to do that every time, but it's also good to sort of verify that you got the correct number of oxygens since we skipped over that. So it's just a good way to kind of check your work. All right, so some general tips. Start with the first reactant and then go reactant by product by product. And if you find that something's in more than one equation, usually this is oxygen, just skip it, and it will usually, not always, but usually work itself out. Okay, so try this one. Pause for a second, try this, and then we'll go over it. Okay, so C2H4 ethene is in equation C, but it's on the wrong side, so we have to reverse C. Fluorine is in multiple equations, so we're going to skip that for the moment. CF4 is in equation B. It needs a coefficient of 2, so we have to multiply this equation by 2. And then HF is in equation A, but it needs a coefficient of 4, so we have to multiply everything by 2. And then our final answer would be negative 2,486 kilojoules. And that would give us the heat of this reaction here. Okay, now, just because we haven't calculated enthalpy enough different ways, let's add one more. All right, so we can calculate the heat of a reaction from the heats of formation of the reactants and products. Okay, so we can take the sum of N, which is the number of moles, times the heat of formation for each product and each reactant. And I think it'll be clearer when you see an example what that means exactly. And heat of formation is abbreviated as delta H sub F, and these are given in table 12 in the data booklet. The heat of formation defined is the enthalpy change when a substance is formed from its elements in their standard states. So an important thing to note here is that if we have an element in its standard state, its heat of formation is 0 because there is no process of forming it from its elements. It is an element itself. Okay. The advantage over calculating using bond enthalpies is twofold. You have more accurate data because it's specific to the substance as opposed to just being an average of all the bonds, and the species don't have to be gaseous. You do need to be careful though when you're using this table because, for example, water, there's data in the table for gaseous water and liquid water. Okay, so you just have to be a little bit careful that you use the right value. Okay, so let's do an example using the data booklet. Now, I went ahead and found these values from the data booklet. I suggest that you go check and make sure you're finding the same values I am. Now, oxygen's not in the data booklet, but that's okay because we should know that it's 0. Okay, so when I'm doing these problems, rather than just trying to put numbers in the equation, I like to write the heats of formation under each reactant and product. It seems like a small step that isn't very meaningful, but it really helps me stay organized when I'm setting this problem up, because this is, again, another kind of problem where it's really easy to make a little mistake. Okay, so start with my equation. All right, so again, I want to calculate everything for products, everything for reactants, and then subtract. And I'm going to be very, very careful when I'm doing this because I don't want to make a silly mistake. Okay, so it's products minus reactants. So CO2 is negative 393.5, and there's just 1 mole, so I don't need to multiply that by a coefficient. Water in the liquid state is negative 285.8. So I have that here, but I multiplied by 2 because water has a coefficient of 2. And then I have to subtract the reactants. Methane is negative 74, and again, there's just 1. Now, oxygen is 0. If that was a real number, 0 is a real number, but you know what I mean. If it was a number that was non-zero, I would have to multiply it by 2, but I didn't bother here because 0 times 2, you know, it's 0. Okay, so then when I calculate this out, I get negative 891.1 kilojoules per mole. So this is an exothermic reaction, which makes sense because it's combustion. Okay, so now we need to talk about entropy, which we abbreviate with the letter S. So entropy is just a measure of disorder in a system. So as we go from solid to liquid to gas, the entropy increases in a system. So that's one kind of clue when we look at an equation to figure out if entropy is increasing or decreasing. Okay, so let's look at these examples. In the first example, the synthesis of ammonia, everything is a gas. But one way that I can tell that entropy is decreasing is that on the reactant side, I have 4 moles of gas going to 2 moles of gas. So that means this system is becoming more ordered, and the sign of delta S, the change in entropy, is negative. Now, for the next example, liquid water going to gaseous water, I have just a change in state of matter. So entropy is increasing because it's going from liquid to gas, so it's more disordered. And then in this last example, I have a solid decomposing to a solid and a gas. So again, we have an increase in entropy. Multiple factors influence entropy in a reaction. The number of particles, particularly significant, we're talking about the number of gas particles, the nature of the particles, and the available energy of the particles. Okay, so we can calculate entropy the exact same way that we calculated enthalpy, using the same table, table 12 in the data booklet. So it's products minus reactants again for the standard enthalpies. Now, an important note about units. Enthalpy has units of joules per mole Kelvin. Now, the other two things in that table, enthalpy and Gibbs free energy, are in kilojoules. So the significance there is that at one point we're going to put them all together, and when we do that, you have to make absolutely certain that all the units of energy and enthalpy are consistent. And I will show you how to do that when we get there, but I just want to say that now, and then say it again, and hope that it sticks. Okay, so let's calculate standard enthalpies. And again, I pulled out the enthalpies from the table and put them here, but you might want to check them. I gave you that the standard entropy of oxygen was 205.2, and on a test or the IB exam, they would have to give you that as well, because these aren't enthalpies of formation. This is just the enthalpy of that substance. It's not a change, it's an absolute value, so oxygen does have disorder associated with it. Okay, so same basic process. And in the end, you get a negative value for entropy. So let's talk about why that makes sense. And double check that you get the same values I do on the math, because you want to make sure you're doing this right and not making a little mistake. Be really careful with your signs. Now, on the left side, the reactant side of this equation, we have 3 moles of gas. On the right, we have a mole of gas and 2 moles of liquid water. So it does make sense that the entropy is decreasing. Now, if we had put, and so we picked liquid water intentionally here to show this a little bit better. If that was gaseous water, the entropy change would be very, very small because we have 3 moles of gas on both sides of this equation. But the liquid water gives us a much more noticeable change in entropy. Okay, so let's look at some examples of different reactions or processes and try to determine if they're spontaneous. So spontaneous in chemistry means that it can happen at a given temperature. It will occur. Okay, so, and I mean, it may need activation energy to occur, but it will occur naturally. So the combustion of methane, we know that this occurs spontaneously because we light Bunsen burners. After a little spark, the process just happens naturally. The second is the example that we're doing in class. We're mixing 2 white solids, and we produce aqueous barium nitrate, ammonia gas, and 10 water molecules, and that happens spontaneously. Solid to liquid water, at room temperature, that is spontaneous, right? If I leave a block of ice on the lab bench, it's going to melt. But liquid to solid water is not spontaneous at room temperature. However, it is spontaneous at colder temperatures. And the dissolution of calcium chloride, which we did in the lab 5.1, is, as you know, spontaneous at room temperature. So, if a reaction is spontaneous, that means that under given conditions, specifically temperature, it will occur. That doesn't mean that it will occur rapidly. So when we talk about kinetics in the next unit, we'll talk about that issue. It just means the reaction will happen. A good example of this is the decomposition of hydrogen peroxide. That's a spontaneous reaction. But if you were to go home and if you have a bottle of hydrogen peroxide in your cabinet, if you open it up, if it's been closed for a really, really long time, you might hear a little gas escape because some of it has decomposed to water and oxygen gas. But it's so slow that it takes, months and months to happen spontaneously. So again, spontaneous doesn't mean it'll happen fast, it just means it'll happen. Okay, so in order to figure out if something is spontaneous, we're going to sort of combine enthalpy and entropy to solve for something called Gibbs free energy. So we need to determine what makes enthalpy and entropy thermodynamically favorable. These are the drivers of the universe. Everything in nature tends towards stability and disorder. So, what types of reactions lead to more stable products? Exothermic reactions. So, a negative value for delta H will be more favorable. Which types of reactions lead to more disorder? That would be reactions where delta S is positive. So again, that's more favorable. So, Gibbs free energy tells us about the total free energy in an equation. So it sort of combines enthalpy and entropy and allows us to determine if a reaction is spontaneous at a given temperature. Okay, so delta G, Gibbs free energy, is equal to the change in enthalpy minus temperature in Kelvin times the change in entropy. Okay, so let's look at 4 hypothetical reactions. Okay, in the first reaction, delta H is negative. So that means this entire term is negative. Okay, delta S is positive. So if this is positive, that means that this term is negative. So that means that if this term is negative and this term is negative, delta G overall must be negative. Delta H is favorable because it's negative. Delta S is favorable because it's positive, and since delta G has to be negative, we know that this reaction will be spontaneous. So an exothermic reaction where disorder is increasing will be spontaneous regardless of temperature. Okay, let's look at the next scenario. If delta H is positive and delta S is positive, or delta S is negative, excuse me, that means this term is positive, and since the two negatives will cancel out, this term is positive. Okay, so delta G must be positive. Delta H isn't favorable, delta S isn't favorable, and it is non-spontaneous. Now, reaction 3 and 4 are a little more interesting. Okay, so in reaction 3, delta H is positive and delta S is positive. So if this term is positive and this term is negative, then it really depends on the magnitude of those numbers and the temperature to determine the sign of delta G. So we could just say it depends, okay? Delta H is not favorable, delta S is favorable, okay? So that means that it will be spontaneous when I maximize the favorable term. So it'll be spontaneous at high temperatures, okay? Now, in the final scenario, delta H is negative, so that's favorable. Delta S is negative, so that's not favorable. And this term is negative overall, and this term is positive. So again, the sign of delta G depends on the magnitude of those values and the magnitude of the Kelvin temperature. So this would be spontaneous at low temperatures, right? Because we want to minimize the unfavorable term. Okay, so let's calculate the delta G, the change in Gibbs free energy, for the combustion of methane at standard conditions and determine whether it's spontaneous. So we're going to actually use 2 methods and compare them. We're going to use delta G equals delta H minus T delta S, and we're going to use the same products and reactants method we used for delta H and delta S previously. Okay, so the same equation we've been using. So first, let's do delta G equals delta H minus T delta S. Now I want you to look really closely. We already found delta H earlier in this discussion. It's negative 891 kilojoules per mole. Now, we also found delta S, and it was negative 242.6 kilojoules per mole, or joules per mole Kelvin. But we need this in kilojoules. So we're going to divide by 1,000 and put it in kilojoules. Okay? This is per mole Kelvin. We need to make sure this temperature is in Kelvin. Okay? And this is at 298. So when we solve this, we get negative 819 kilojoules per mole. Okay? All right, so that's method 1. So it's spontaneous. We can also use the same process we did before, products minus reactants. I don't have the equation written here, but you can go back and note the delta G values. And since this is the change in Gibbs free energy, again, of formation, for an element in its standard state, it will be 0. So oxygen is, again, 0. And we would get the same answer. Now, we would not get the same answer here if we weren't doing this at standard conditions. So if the temperature was different than 298, it would make way more sense to use this first method, because then we can change the temperature. This is always going to be at standard conditions. So typically speaking, we tend to use this. Another really cool thing you can do with this equation is you can figure out the temperature at which something becomes spontaneous. Okay, so if I want to figure out the temperature at which a reaction becomes spontaneous, I can say, okay, delta G negative means spontaneous, right? So if I set delta G as 0, that's the point at which it will change from positive to negative. So if I set delta G equal to 0 and solve for temperature using delta H and delta S, I can actually calculate the temperature at which a reaction becomes spontaneous. Now again, that would only be for the situations where it depended on the temperature. If it's an exothermic reaction where disorder is increasing, it's always going to be spontaneous regardless. Okay? A lot to process. You're starting to get a lot of different ways to calculate change in enthalpy, so it's important to try to keep those straight. Make sure you always pay attention. If they reference a table, turn to that table right away, and that'll help get you in the right mindset to use the right method. Okay? Good luck!